So just before homework questions, when we were looking at this issue yesterday, in 10.1, when we came up with this formula for the nth partial sum versus the formula we came up with the nth partial sum for geometric in 10.3, the reason that when we were simplifying this one, it didn't quite work out to this formula here is because in 10.1, that series started at 1, and this series here starts at 0. So we get this nth partial sum formula when k starts at 0. The nth partial sum formula when k starts at 1. We have a different, just in general, I mean, just like the sum of a times r to the k when k equals 1 is ar times 1 minus r to the n all over 1 minus r. So what's different here is our initial term, right? That a is your initial term. When the sum starts at 0, it's the sum k equals 0 to infinity on ar to the k. So the initial term when it starts at 0 is a. The initial term when the sum starts at 1 is ar to the first. So that's why that's a different formula. So I didn't mean to cause any confusion. I didn't realize we were summing from 1 to infinity in 1. But that's the reason they're different, and that's the reason it didn't work out. So does that make sense? Anybody have any questions on that? So the formula is still valid. It's just the formula we justified here with our geometric is when it started at 0. If the geometric starts at 2, then the nth partial sum is ar squared times 1 minus r to the n over 1 minus r and so forth. All right, are there any questions over the homework? We did finish 10.3 last time, so we'll start 10.4. I recognize we are a little behind. If nothing else, once we start chapter 11, we should be able to catch up because I've got chapter 11 broken down into one section a day, but I don't know that we'll actually need that because a couple of those sections are short, so we can catch up sometime during chapter 11. So in this section, we're going to look at a few tests, two main ones, the divergence and the integral test. And then we'll also talk about a p-series test. The p-series test sort of falls out from the integral test. So they're kind of together here. You know, this is the p-series is a result of the integral test. Some notation, when you see this, just the sum of a sub n with no bounds here, that is taken to be an infinite sum. So they'll shorthand that notation to mean an infinite sum from 1 or wherever. And in the next, well, in this section, I think the next one too, but in this section for sure, we restrict the terms of our series to be positive. In 10.6, we'll start looking at ways to test an alternating series for convergence. But now the assumption is that our series just have positive terms. And a reminder that the leading terms of an infinite series are the terms that have a small index. And when we say the tail, or if we say the tail, that's the terms with a large index. So in really any infinite series we look at, the tail is what determines whether that will converge or not. It's not the terms at the first of the series, if you will. It's the terms. It's the tail of the series that implies convergence. Some properties of convergent series. Hopefully, some of these are fairly intuitive. A couple of them we've seen before. Like number one, if we have a convergent series that converges to capital A, and C is any real number, then if we multiply that convergent series by C, it still converges. So it would affect what it converges to. It doesn't affect the fact that it does converge or diverge. Okay, so like for instance, the series from k equals 0 to infinity of 1 over 3 to the k converges. And so like whatever constant we want to use, it doesn't matter. We'll just say that this sum from k equals 0 to infinity of 100 over 3 to the k also converges, or 1,000 or 1,000,000 or whatever. So multiplication by a real number doesn't affect convergence or divergence, but it does affect what the series would converge to. That's kind of what we get in 1 or 2. Property 3 deals with that if we add or subtract two convergent series together. So it says that the series for A converges to capital A and B converges to capital B. Then if we add those two together, A plus B, it will converge to, or A plus or minus B rather, it will converge to capital A plus or minus capital B. Does that make sense? Does anyone have any questions on that? Okay. Property 4 says that if we've got a convergent series B and a divergent series A, and we add those two things together, then we have a series that diverges. Add or subtract. Now, this could work for more than just two series. It's just a very general statement. So if we had like 5 series added or subtracted together, but one of those diverge, that means the whole thing, the whole sum or difference would diverge. And property 5 says that we've got some positive integer n, or m rather, and we've got a series of a sub k from 1 to infinity, and the same series from that positive integer m to infinity. Either both of those things will converge or diverge. And what that means is that if we shift the index, if we start one series at 1 and say that converges, for instance, then another series started at 100 or 1,000 would still converge. It converges to different things, but shifting where we start a convergent series doesn't affect the convergence. Remember, what affects convergence is the tail. And if we start at a different location, that's totally fine. It's a different series, but it still converges or still diverges. Okay, so it says whether a series converges or not doesn't depend on a finite number of terms added or removed from the series. The only thing that's affected is the value itself. So again, I'll just stick with this example. The sum from k equals 0 to infinity of 1 over 3 to the k, we know that converges. So does the sum from k equals to 100, from 100 to infinity. Of course, they would have a different value, but still both converge. Likewise, if we said that if we started with the sum from 100 to infinity of 1 over 3 to the k, and we knew that converges, and we subtract all of those terms and start at 0, that series still converges as well. So it says whether we take away or add to the number of terms in a finite sense, it's not going to affect convergence. Okay. So are there any questions on those properties?
I think we've utilized a couple of them in the last section in 10.3 when we were doing that, the telescoping series. And we pulled out a constant, figured out what I think it was a half, we factored out, right? And then we just determined the sum of the series itself. Once we determined that, we just multiplied by a half. So that's kind of what we were utilizing. Property, I guess it was 2 specifically. Okay, so I guess really the first actual test we look at is the divergence test. Either the series is geometric, and if the ratio, absolute value of the ratio is less than 1, we can determine what it converges to. Or it's telescoping, which we can collapse a lot of terms, find the nth partial sum, and also state what it converges to. So now we're going to get into more like general tests to determine whether series converges or diverge. And the divergence theorem says, or the divergence test says that if we have a convergent series, then what we know is that the terms, or the tail, approaches 0. So equivalently, and what we're going to use in practice when we apply the divergence test is if the limit at infinity on the term itself, this a sub k, not the sum, just the terms, if that limit is not 0, then we can say the series diverges. So just be mindful of this statement. It's an if-then statement. It's not if and only if. We can't read it both ways. So the divergence test will only tell you if a series diverges. If the limit here of a sub k is not 0, like if it's 10 or 1 or whatever, then the divergence test is inconclusive. You might have something that diverges, but you also might have something that converges. I'm sorry, if it is equal to 0, rather. So it cannot be used to determine convergence, only as its name implies. It's just a divergence test. Okay, so another way we can say that is if the limit at infinity on a sub k is equal to 0, the divergence test is inconclusive. Which means that you need to use another test. Okay, so just justify this by saying we're going to let S sub k be the sequence of partial sums for the series, the infinite series of a sub k. And our assumption is that the series converges. So assume the series a sub k converges. Then what we have is that the limit, we're using k, so the limit as k approaches infinity on the kth partial sum is something, we'll just call it L or capital S or whatever. Does everybody agree with that? If we know a series converges, then we know that like in this case, this formula for the partial sum, the nth partial sum has to converge to something. Just like with the 1/3 to the k, we had that nth partial sum, or even in 10.1 we had this thing converging to 1/2, right? We have a convergence series, the kth or the nth partial sum has to approach something finite. Okay, and so what that also implies, you got a convergence series, then this is true. And then sort of the implication of this statement here, the limit as k approaches infinity, is that the limit as k approaches infinity on the previous, the k minus 1 partial sum, would be what? Would be what?
The same.
The same, right? If we're way out there, close to infinity, whatever that means, and that partial sum is equaling some number s, then the one right before it has to be s as well. Does everybody agree with that? Does it make sense? Okay. So this is equal to s. I'll pick that up if you don't have it. Okay, so then what we can say is that first, if we look at the kth partial sum minus the previous partial sum, what would that give us?
0.
Yeah, zero on the left hand side, but only 0 when we take the limit of the left hand side, right? So like, what if I said, what's the, like, for any given series, what's the fourth partial sum minus the third partial sum? What would that give you?
That should be the fourth term of the series.
Yeah, it's just the fourth term of the series, right? So it's s sub k minus s sub k minus 1 would give us which term of the series?
Just the fourth term.
The k.
Or the
Right, so I don't know, just say we had our third partial sum was 1 plus 2 plus 3, right? And the fourth partial sum is 1 plus 2 plus 3 plus 4. When we subtract these two together, from each other rather, those things vanish, and what we have is just the fourth term of the series. You can do that with it doesn't have to be 1, 2, 3, and 4, that's just a specific example. Okay, so if that's true, if that statement holds for, you know, any series, then we'll take the limit of both sides. Okay, and as we noted, the left-hand side is just s minus s, or L minus L, which is 0. So as k approaches infinity on the kth term, it's approaching, the kth term rather is approaching 0. And so what we did was we started off with our assumption. We're assuming that the series converges, and what we've shown is that if something converges, the kth term at infinity as k approaches infinity has to be 0. But again, in practice, we're actually looking at the contrapositive of the divergence test. So remember the contrapositive, if you've got a true statement, the contrapositive is always true as well. And so what that means is if we have a statement, if the series converges, then the limit is equal to 0. So like if P, then Q. The contrapositive is if not Q, then not P. So you flip the argument and you negate both statements. So just to give you an example, and it's a really common thing if you have a theorem in math, especially if it's just an if-then statement, you can always flip the statement and negate the argument in the conclusion, and that will still be true. So let's look at just a language example, I guess. So if I live in Denver, then I live in Colorado. Oops. I might have one too many. But anyhow, the contrapositive, we'll write this here. The contrapositive of if I live in Denver, then I live in Colorado would be what? If I don't live in Colorado, then I don't live in Denver, right? If I don't live in Colorado, then I don't live in Denver. Okay. Huh? Is there? All right. Who knew? There's a Paris, Texas. It's glamorous. Okay, so true statement, I live in Denver, I live in Colorado. Contrapositive, also true statement, right? The thing that's not always true, and it's really conditional, is the converse. I'll do this in a different color. The converse of a statement is just when you flip it. So the converse of if I live in Denver, then I live in Colorado would be if I live in Colorado, then I live in Denver. So that's not always a true statement. But if you're continuing on in math, which I assume most of you will, it is a useful thing to utilize when you're presented with a theorem. If it's an if and only if theorem, that's fine. You can read it both ways, but you could still flip it and negate it. So when I think of contrapositive, I think of that Missy Elliott song. I don't know. I guess I'm older than y'all. But she had a popular song in the early 2000s. Huh? No thanks. I'll pass on that. All right, so really when you see a series, it may or may not say, like, use this particular test to determine. But I would recommend you start off with the divergence test because it's a really simple test. And if the limit is not 0, the series diverges and you're done. There's nothing left to do. But anyhow, use the divergence test to determine if the -1 to the k times k over k plus 1 converges or diverges. So remember, the divergence test says that we compute the limit at infinity on the kth term, which is just explicit to the summation notation. So, the -1 to the k could be a little potential of an issue, I guess, if you looked at it too thoroughly. What about the k over k plus 1? As k approaches infinity, that approaches 1. Okay, so we'll just say that this is equal to, this thing approaches 1. What happens, though, with the -1 to the k? It's positive or negative, right? It never actually hones in on a positive or negative. Depending on where you're at, it's either positive or -1, right? So that's either positive 1. I don't know how to write this out technically, but yeah, so plus minus 1, I guess, times 1. Either way, the result of that limit, and it does depend on where you're at, but either way, the result of that limit is either 1 or -1. So is there anything we can conclude from the divergence test? It diverges, right? If it's 1, it's not 0, diverges. If it's -1, not 0, diverges. So the conclusion then is that this limit is not equal to 0. And anytime your kth term at infinity is not 0, that's enough to say that that series does not converge, diverges. And And of course, ultimately, we're not interested in divergent series. We're interested in series that converge to a specific thing. In chapter 10, more so in chapter 11, like we said, we're interested in series that actually converge to a particular function. If it diverges, it's not useful. Because just think of the term convergent is saying that this infinite thing is equal to this other thing. So the convergence guarantees us equality. It's kind of interchangeable. Okay, how about excuse me? How about the sum from 1 to infinity of 1 over the square root of k? What would the divergence test tell us? So that limit is 0. What does that mean? Yeah, it doesn't diverge. So really, we gained no information here. The series could diverge, it could converge. So it's inconclusive. At this point, we don't really have any other test, but we would need to use another test. So we don't know anything about convergence or divergence there. Any questions on that? Okay, use the divergence test on 2 plus 5 to the k over 2 to the k. What did you come up with? Diverges?
Yeah.
So I think the use of growth rates here would be extremely efficient. Well, let's just go ahead and write all of it out first. So at infinity, we can just look at leading term over leading term. And by growth rates, 5 to the k grows more rapidly. So this is infinity. The growth rates. So the limit is infinite, clearly not 0, so it diverges. Series diverges. All right, easy enough? So that's the easiest test that we have. The other ones deal with more involved things. We'll have to let me see what's next. We'll have to come back to that. I do have a typo here. The nth partial sum. Cross that out. You can't. There isn't a known formula for the nth partial sum here. So let's look at this, and then maybe we'll look at the next test. But note here that the divergence test on the harmonic, that they call the harmonic series, k approach infinity, 1 over k, is equal to 0. So the divergence test is actually inconclusive. Which means that series could converge or could diverge. And maybe you can remember back when we first started that improper integral chapter in the last unit, that we did look at the integral from 1 to infinity of 1 over k and said that diverged. So the next test is relating an integral to a series. They're closely related, but they're not quite the same, right? Because the integral considers a continuous function. It would be all of those values. A series is only concerned with the integer value or the integer inputs of that particular function, right? So like if this were the continuous function, the series is only looking at these things here, not everything in between. So like if we look at the area under the continuous curve like this, and then compare that to these discrete points that are added up, they're closely related, but they're not identical. Okay, so first 4 partial sums. We're just going to look at the first 4 terms and then add those together. So we have 1 plus a half plus a third plus a 4. So the first partial sum is 1. Second partial sum is 1 plus a half, which is 3 halves. Third, 1 plus a half plus a third. And what is that? That's 2, 5. What is that? 6. 11. And fourth. Get there. 25 twelfths. So the divergence test was inconclusive, but what it does show us is that what? Well, not quite. If this term, the kth term of this series, is approaching 0, then what do we know about the terms? They're getting smaller and smaller, right? Because we're literally just computing the limit at infinity on the kth term of that series. So, you know, if we came out here and to that term, right, plus the next one, et cetera, these subsequent terms are all getting smaller than the previous term. That's what that limit tells us. But again, just because the terms are getting smaller and smaller, eventually approaching 0, that doesn't mean that we have convergence. And this is usually like the quintessential example to say just because the terms get smaller doesn't mean that a series converges. Okay, so maybe we can pause on that for a moment and look at the integral test. And so the integral test says that suppose f is a continuous positive decreasing function for x larger than or equal to 1. We're going to let a sub k equal f of k. So that's our discrete version of the continuous function for 1, 2, 3, etc. Then we've got the sum, infinite sum of a sub k and the integral of f of x dx. And this, remember, this f of x here is this thing here, just replaced with a k. Either both converge or diverge. So in other words, if we compute this integral and it converges, then that will tell us its corresponding series converges. If the integral diverges, the corresponding series diverges. But the value of the integral in general is not the value of the series. So like if I come up with the value of this improper integral to converge to like 3, I wouldn't say the sum is also converging to 3. All I would say is that since the integral converges, the series given converges. We're not going to actually prove that, but the proof is based on this inequality where we have our sum starting at 1. So if we looked at that sum and stopped right before n, the n minus 1 term, that sum is larger than the integral or equal to. If we start our sum at 2 and stop at n, then that sum is smaller than the integral, because we see here that this would indicate that we're these right Riemann sums under approximating the area, and this series here give us left Riemann sums which over approximate the area. So what we end up with is binding this integral in between these two series, an under and over kind of thing. And from there, the proof kind of continues on, but that's the idea. Specifically why, see this is less than or equal to, so sometimes the integral does equal the series value, but there's really no way for us to know that. So all we're going to attach is convergence or divergence to this test. Let me talk about these conditions here. These conditions for the function, which correspond to the series that you're given. I would say in some way, shape, or form, you need to justify that those conditions are true. Like so, if an exam question is use the integral test to show that this series converges or diverges. If you're going to go follow through with this test, somehow you need to justify those three things, because those are the assumptions of the function or the series. And I hope that the continuous and the positive are both should be relatively straightforward. Remember, continuity is essentially depending on the function's domain. Positive, it should be really clear to you when you look at a sum from like 1 to infinity, if those terms are positive or negative. So those two things should be relatively clear. Decreasing, maybe not always the most straightforward one to deal with. Sometimes, depending on the series, to test whether a function is decreasing, how would we do that? Or how have you done that in the past?
Like, test out numbers.
Yeah, you could test out a few numbers, but what would be the issue with just testing a few numbers? Like it could change, right? Especially, well, I won't say that yet, but drainage. Yeah, the first derivative tells us where a function's increasing or decreasing, right? So like whenever you're given a function, I don't know, whatever it is, like where is that function increasing and where is the function decreasing? You look at the first derivative figure out where the first derivative is 0, then you put that there, and then you test here, maybe it's positive, maybe it's negative, whatever. And you say, okay, well, after c, my first derivative is always negative, therefore, after this value of c, this function is always decreasing. I know that's not accurate for the example I wrote, but let's see. So sometimes you might have to use or justify this decreasing piece with the first derivative. So I'll just put this here just to remind you, maybe vaguely. It might have been a while since you've done this, but. All right, so computing the integral, if the integral converges, the series converges. If the integral diverges, then the series diverges. That's what the integral test is. Okay, and that note here is saying that the integral test, although it says that f is a continuous positive decreasing function, it doesn't say that it always has to do that. The way we should interpret that is that after some point, after some value in that series, maybe it's k equals 5, maybe it's k equals to 100, but eventually the thing will be positive and decreasing. So it's okay to have like a few negative terms in there, but eventually it has to have positive terms. It's okay for it to increase and then decrease, but eventually it has to just decrease. If you go through the proof, their assumption is that it's always continuous positive and decreasing, but in practice, the tail is really what matters. So eventually this has to be positive and decreasing, continuous. And that's what that note is saying.
So there's no proof for just the tail end justifying that?
For which part?
For that, like you said, like it could do funky things at the beginning, but the proof doesn't indicate that.
Yeah, the proof just assumes that it's always doing that. It doesn't say, the proof doesn't say consider this particular function decreasing after some value. It just says assume f is continuous positive and decreasing, and then just runs with it. So their assumption is that it always behaves that way to justify the integral test, but in fact it doesn't matter if some terms towards the beginning are fluctuating.
That's something they found experimentally.
Yeah. Because again, the whether a given series converges or diverges, it wouldn't depend on like a handful of terms. Like, even if this were like 100 terms where it was like positive, negative, it's not going to matter. What matters is out here to affect the convergence. Because even if you summed up the first 5 billion terms and you have this like massive number, but eventually these things start behaving in a certain way, then it would converge under specific circumstances. But the beginning of the series doesn't really matter. Okay, so use the integral test to determine if k over e to the k converges or diverges. And then, just for reference here, the divergence test, maybe you can see right away, but the divergence test is inconclusive. So we don't know if it converges or diverges off of this. And so our series is k over e to the k, so we're going to let our function of x, our continuous function, be x over e to the x. And keep in mind that since the series, I do want to point this out, I forgot. But the integral test, that lower limit of integration in the integral test, matches the lower index of your series. So like if this series started out at 5, we would want to integrate from 5 to infinity. So I'll go back there and make a note here. So this has to match that lower limit. All right. So since we're looking at the function x over e to the x coming from the series k over e to the k, the series starts at 1. We're only concerned with this function f of x on the interval 0 to infinity. So oftentimes the interval can be really helpful, especially for maybe for all three, but for the positive part, usually it's helpful to recognize what interval you're working with. Okay, so we're going to justify those three things. Is f of x positive? So that's pretty straightforward, right? I'm plugging in 1, 2, 3, 4, 5, 6, and all the numbers in between. E to the x, always positive. X, not always positive, but on the interval from 1 to infinity, certainly x is always positive. So, there's really little to do there. I'll just say something to that effect. I guess it doesn't matter what order we apply these, but we need to address all three. Is that function continuous?
Yes.
Yeah. So we're only dividing by e to the x, and we know e to the x is never 0. And finally, is that function decreasing? On 1 to infinity. So is there a quick way to tell that? So e to the x is growing much more quickly than x. So if we have 1 over e, 2 over e squared, 3 over e cubed, but you'll have to justify it somehow. So we'll say, we don't know, but the first derivative of that function is plus second derivative of the first. So the first derivative is that. Which is that. And this is equal to 0. When x is equal to 1. So then we come up with our chart for the first derivative. Again, the function's defined on 1 to infinity, so we'll test the interval 1 to infinity. That's, in that in that realm would be our critical point. So we're just going to pick some number out here, I don't know, say 2, and evaluate the first derivative at 2. So e to the x is always positive. A positive times 1 minus 2 is a negative. Positive times a negative gives us a negative. So, you know, there's those after 1, that function is, the derivative rather is always negative, which means after 1, that particular function is always decreasing. Whatever, it's a negative number, I don't know exactly what it is. So, our conclusion is, yes, it's decreasing. If you want to use, I think you should know this for sure, this procedure. But if you did compute the limit as x approaches infinity on x over e to the x, it's approaching 0. So you know whatever that function looks like, we do know that it's eventually approaching 0. So eventually, this term here is less than the previous. This term is less than the previous, right? So if the next term is less than the previous term, it's decreasing. So I know it seems like a trivial thing, but the entire test is based on these 3 conditions. If these 3 conditions aren't met, if either one of those 3 conditions is false, then the test really isn't applicable. So it's not a trivial thing just to say, okay, yeah, I'm just going to assume all that's true for this thing and use the integral test. Because if one of them's not true, you use the integral test, whatever result you get is going to be inaccurate. So we justify those 3 conditions, continuous, positive, and decreasing, and then we compute the integral. The integral from 1 to infinity of, we have x over e to the x. And so this is where like the stuff we did in chapter 8 can really come in handy. If you look at a series and say, oh, I think I can integrate, that looks like a pretty easy integral, or it looks like something that's easy to integrate, then the integral test is a viable candidate. So how are we integrating x e to the negative x? By parts, u should be x dv e to the negative x dx. So then du dx. V is the antiderivative of dv, negative e to the negative x. I think this was on our exam. So our integral then, I'll write it down here. The limit as b approaches infinity of the integral from 1 to b on x e to the negative x. And maybe we should just figure out what this integral looks like and then put the bounds in, because we'll get an additional antiderivative. So we have u times v minus the integral of v times du. So our antiderivative then is negative x e to the negative x minus e to the negative x.
Wouldn't that, in the integral, be negative e to the negative x dx?
Yeah, that would be a negative, and then it would make
Oh,
the,
yeah, okay.
yeah. So. Okay. Oops. No, I had it right. That's right. That makes that right. Okay, so plugging in b, letting it go to infinity, and plugging in 1. Yeah, I guess we'll do the limit part first. So we've got negative b times e to the negative b minus e to the negative b for that limit. There's f of b minus f of a. So as b goes to infinity, what does negative b over e to the b approach? So think about it as maybe negative b over e to the positive b. Approaches 0 because e to the b grows more rapidly. If you end up with infinity over infinity here and forgot about growth rates, then that's when you have to do L'Hopital's rule. So this thing, we'll just rewrite these two. What do we have? We have minus 2 of those. Minus a minus 2 of those, rather. So both of these here approach 0. We'll just write it below. This is 0, and this is 0. So we have that integral converges. We really don't care about the value of the integral because the value of the integral is not the value of the series. Okay, so basically then our conclusion is therefore, since the integral converges, so does the series. Does anyone have any questions on that? So with the integral test in mind, let's go back to that harmonic series. I said that even though the terms approach 0, the divergence test was inconclusive. But if we looked at the integral of 1 from 1 to infinity of 1 over x dx, and here we're just talking about this function on this interval. clearly it's positive on that interval. Continuous on that interval, yeah, because x is not equal to 0. And is the function decreasing? Yeah, the first derivative of that is negative 1 over x squared. Negative 1 over x squared is always negative. So since the first derivative is always negative, the function itself is always decreasing. And so you might remember this one as well, where it said the antiderivative, natural log of x, evaluated from 1 to b. Which diverges, right? Because the natural log approaching infinity also approaches infinity. So it diverges, 1 over x rather, the integral diverges, which means the series, the harmonic series diverges as well. So just because the terms go to 0, and eventually we are adding up 0 plus 0 plus 0, it just doesn't happen fast enough. So that's the theorem here, the harmonic series 1 over k to the first diverges, even though the terms of the series tend to 0. There's other proofs for this that it diverges. We just use the integral test. Another one's really clever in how it groups up the terms. And it says if you group it up in this way, the sum of those individual terms is always 1/2. So you're always adding up a half plus a half plus a half forever. So there's various ways people have been clever with trying to show that diverges. But the integral test is sufficient. All right, so that's the series you should remember when you compute the limit on the terms and it's equal to 0. Before you say it converges just because the terms go to 0, you got to remember that one. I mean, you just remember it in general, but this is the classic counterexample to that. All right, do y'all have any questions on what we've done? I would highly recommend that you look over these tests, because in 10.5 there's 2 more tests, in 10.7 there's 2 more tests, and in 10.6 there's another test. So you end up with like 5 tests pretty quickly, and they all have their own individual conditions. You've got to know, like, if it turns out to be this, then what does that mean about convergence, etc. So I would recommend keeping up on those. We'll take a break if y'all don't have any questions then.
Yeah, see, I just plugged in.
That's my problem.
You have
I've never applied.
Yeah, they
Well,
only,
But it's easy
no,
to
there
draw.
should
they only 2 of 4, so.
There's like a bunch of scholarships.
All right.
Yeah.
So the next series that we can quickly identify if it converges or not is the P series. So if you've got 1 over k to a power, and that power is larger than 1, then you have the series converges. Larger than or equal to 1, it diverges. So this is just a result of the those 1 over k to the p, the integral of that is how that test comes out. So I don't know that I would necessarily call it a test. It's just a particular type of series. And you can see that when p is equal to 1, we have 1 over k, which is the harmonic series, diverges. So use the p-series test to determine whether 1 over k cubed converges or diverges. Those of this form, 1 over k or n to a power, should be fairly quick, since the power is 3, which is larger than 1, the series converges, sorry. How about 2 over square root of k? Converge or diverge? Diverges. And again, that constant multiple of 2 doesn't matter. 2 times the series of 1 over k to the 1/2. The power is 1/2, which is less than 1, which means that it diverges.
Did you say K always has to be 1 in these cases?
No, k doesn't always have to be 1. And again, we can go back to that property number 5 on that first page, where if we add or subtract a finite number of terms, it won't affect the actual convergence. So this could be the sum from k equals, 100 to infinity. It'd still converge, or diverge, sorry. But how about example 8? So can we say it converges because the power is 2? So we wouldn't necessarily have to compare it, but 1 over k minus 1 squared is definitely not 1 over k to a power, right? So the trick here is to just shift it. I think we might have mentioned this in passing in an example or two, but if we're gonna add 1 inside here, inside the thing that we're summing, then does anybody remember what we have to do to the index? Do we add 1 to that? Yeah, you subtract 1. So if you're gonna add 1 inside the thing you're summing, you have to subtract 1 here. And that way it'll fit the format of a p-series. So we would go from 1 to infinity of just 1 over k squared. So I mean, you could come up with a bunch of different examples like that. If you shift it over, as long as that power is larger than 1, we have convergence. But I mean, it's worthwhile knowing that technique, because as we see, we'll get more and more tests, and it becomes a little more convoluted. Because sometimes the more choices you have, the more confusing it can be, right? You ever stand in the grocery store, like looking at all the cheese, say which cheese should I get? There's like 100 different cheeses. Sometimes you just wish it was just one cheese there. So anyways, the more tests we get, sometimes convolutes the process of like, okay, which test should I use, right? Okay, how about the p-series test to determine if k to the e over k to the pi converges? What we need to do there?
Take out the k to the e.
Well, so k to the e is still a power on k though, because so that's actively being summed at each time.
You just rewrite that as 1/3 K pi minus E.
Yeah. So just properties of exponents, we can rewrite this as 1 over k to the power of pi minus e. Therefore, we've got it in the form. And then we just got to figure out, is that power larger than 1, less than or equal to 1? Our power is pi minus e, less than 1. 2.14 minus 2.78, 2.718. Power is less than 1, therefore the series diverges. 2.71828.
Isn't 5 the last letter?
Yeah.
Oh, yeah.
Power less than 1 series diverges. Now, I just worth pointing out on these examples here, if we were to use the divergence test on all of these examples, the divergence test is inconclusive on all of them, right? All of the terms approach 0. First one converged, second one diverged, the third one converged. Divergence test on this would give us what? What would the result of the divergence test for number 9 be? Zero, right? So if I looked at the divergence test, the limit as k approaches infinity, I guess there's a couple of ways to look at it, but since k to the pi power is larger by growth rates, that limit would be equal to 0. So in all of those, we would have an inconclusive test with the divergence test. Some of them converge, some of them diverge. Okay. Any questions on that? Oh, we already did that. So here's what we've looked at so far. We've got a geometric series test, a divergence test, an integral test, and a p-series. And those are the conditions for convergence or divergence. We will be adding to this, so it's not fully complete, but it's where we're at so far. All right, choose your test. Determine whether the given series converges or diverges. So, it's basically we can start out by asking, is it geometric? Is it telescoping? Probably not. No, not a friendly thing we would try to do partial fractions on. It's polynomial over a polynomial. So just start with the divergence test. see what that gives us. Divergence test. What's the limit at infinity on this term? 1. So since the limit at infinity on the kth term is not 0, we can say that it diverges. So that's kind of how I would start with if I were given something and I didn't know, if it didn't specify a particular test to use. If it's geometric, you should be able to recognize that pretty quickly, tell what it converges to. Telescoping, pretty easy to recognize. Even if they're sort of like in disguise where we have to use partial fractions, it would be of the form, something over a polynomial as well, right? So when you have like repeated factors, repeated linear, etc. I think those should be fairly easy to recognize at this point. Otherwise, if it's not, just start with the divergence test and then go from there. The divergence test was inconclusive. Maybe we look at that and say, well, is that something that looks easy to integrate? Maybe not. Maybe a U substitution would work there. It's not p-series, so at this point then we're stuck, right? What else could we do? So we'll add on to our test bank. But we're fine for now. Wait, is there anything else?
Actually,
So what about this one? Number 12.
because it's K-squared.
Over k squared. Yeah, I mean, we can kind of look at it sort of asymptotically. It would behave like 1 over 9k squared. But it's not in that form. It's not just 1 over 9k squared. So we can't just say, oh, that's a p-series. The leading terms are this, right? The p-series doesn't apply to just a leading term. So fortunately, it's not that straightforward. Yeah, partial fractions. So partial fractions here in the hopes that, you know, A is some number and B is the negative of that number. Or if they're different, that's fine too, but the only way telescoping happens is if you have positive and something that's negative, where you get that cancellation. So I think we'll forego working this problem because we're so far behind. We've seen an example of something like this already. So partial fraction decomposition. And I'll just write some of the steps down if you're gonna try to work this at some other point. So when you break that down, your A is 1/3, and that's over the 3k plus 1, and your B is negative 1/3. 3k plus 4. So I think with that, then like with the telescoping series, right, you write down the first few terms and or the last few terms and figure out what cancels. With telescoping series, you can find an explicit formula for the nth partial sum. Let me see what that should be. 1/4 minus 1 over 3n plus 4 is your nth partial sum. And bear in mind, when I worked this, I took out the 1/3. So, you know, it's really this. If you want to leave the 1/3 in, you can. It doesn't matter. I think it's easier for, you know, the purposes of writing out each term, just to leave the 1/3 out. So this series would converge to a 12th. This series. Geometric and the telescoping series are the only ones in general that we can determine with these particular methods what it actually sums to. So one's 12. Okay. So if you do try to work that and get stuck, just please ask. All right. What about 10 over k squared plus 9? Take out the 10. All right, so we'll take out the 10. Is that a P series?
No shift.
Yeah, we could shift it over. We could subtract 9. We'd have to add 9 to our index. Subtract 9, add 9. Converge or diverge? Yeah, P is larger than 1. Series converges. So we can shift it over. If you didn't remember to shift it over, divergence test here is inconclusive, right, which is 0. It's not geometric. It's not telescoping. Does that look like a function we can integrate? Yeah, what's the integral here with 1 over x squared plus 9? No, not natural log.
1 over x plus 9.
What'd you say, Patrick? Inverse tangent, right?
Wait, what? Oh.
Inverse tangent. So we could do the integral test on that. Verifying those 3 conditions, integrating this as inverse tangent. Do you remember what the inverse tangent was as the argument approaches infinity? Yeah. Yeah, pi halves. I guess we'll use B, but yeah, just a reminder. So you would get a finite value here for this integral. So noticing that we could shift it saves quite a bit of time. Verifying that it's positive, continuous, decreasing, finding the antiderivative, computing the limit, and it's pretty tedious. But you would get a finite integral here if you were to integrate it. Yeah, so that's all the tests we have. We've run through them there. Any questions on?
Why we do 2 tests?
We didn't. One test, if you do one test and tell that it converges or diverges, that's it. But just showing that we could use another test if we fail to see that we could like shift it over or something. Yeah. How about 1 over k over k square root of k squared plus 4? Are you just guessing? How do you know?
Because it's K over K.
It's k over k. So divergence test then. It's I guess is what you mean, Jack.
Yeah. You get infinity over the square root of infinity squared.
Okay, so let's see what happens here. remember at infinity, we can look at leading term over leading term, right? That plus 4 under the square root for sufficiently large k really contributes nothing, right? So this is, in the sense of a limit at infinity, this is equivalent to this, which is equivalent to k over k, which is 1. So the divergence test, our limit is not 0. Therefore, the series does not converge. So I know that, like, it's clear that some of you are able to look at it and kind of have a intuitive feel for, all right, this is why it's going to diverge, because it becomes k over k, or whatever your reasoning is. Please make sure you're justifying that somehow on the exam, though. Like, if you just say diverges, there's not a lot I can do to help you out. But I think it is good to develop some intuition, for sure. Okay, I think that's it. Yeah, the end. Any questions on 10.4?
It's always how that
Just be mindful our schedule. We're covering 10.5 next, and then we're going to jump to 10.7, and then come back to 10.6. If you're printing the notes and stuff.
I got a question on that.
Sure.
One we did earlier. The 10 over k squared plus 9. Why can you, so I'm just wondering about the k squared.
Okay.
Does that affect this at all? Because I'm just seeing you're just taking the 9 out that's next to it.
Yeah. So like we had to subtract 9 to the thing we're summing, so we had to add 9 to the index.
Right, which just shifts it over.
Yeah.
Right, so you're moving the index for your starting point. But, in the first example, it was just k plus a number. And so that makes sense to just take that number out, but when it's k squared, I'm just trying to understand why you can still do that. Because if you're shifting k, that's still inside the square.
Oh, okay. Yeah. Yeah.
So why can you do it with a number that's outside the square?
So why isn't it started forwards?
Yeah. Suppose we should look at that. Yeah, I guess without writing out the terms, it's hard to see. Let's go down here and write out. Because, yeah, it's not going to be the same, is it? So already we have, this is 1 over 100. And this is 1 over 10. So that would be the 10th term. Let's see what the 10th term is here. 1 over 2. 4, 16. Wait. That's wrong. That's 3 squared plus 9. It's 18. And that one is 16.
It's just increasing by odd numbers now in the denominator.
Yeah. 1, 2, 3, 4, 5. 25.
5, 7, 9.
We have 30. 1, 2, 3, 4, 5. 36 plus 9.
45.
I'm losing my place.
Plus 3, plus 5, plus 7, plus 9. Yeah, the numerator increases
Yeah.
by the next odd number.
1, 2, so it's 1, 2, 3, 4, 5, 6, 36. 35, is that right? No.
45.
Sorry. Oh, man, it's such a long day. 1, 2, 3, 4, 5, 6, 7, either the 7th term, 7th term, 8th term, 9th term, 10th term. But I think it's not going to be the same, right? Our 10th term is 1 over 100, right? So then, what that tells us is that we overlooked the fact that we can't just subtract the 9 like we did to shift it over.
Which means we use comparison.
There should be
Plus 3, right?
this, if it were this instead, because we're squaring all of it, then we could subtract the 9 and add 9 to the index. Yeah. Is everyone all right with that? Does that make sense? Okay, so yeah, turns out we can't do that.
Well, can't we just turn it into k plus 3 squared? Or no, because it had middle term.
Oh, yeah, that middle term. Okay, so we should get rid of that. At least this part anyways. Okay, so then turns out I have to use the integral test after all. Thanks. Okay, then. All right, I think we'll just leave that alone. All right. 10.5. We're going to look at comparison tests. So there's 2 that we're looking at. The comparison test, maybe we should call the first one a direct comparison test. And then a limit comparison test. So a direct comparison test is when we take the series that we're given, choose something else to directly compare it to. And so when we see this comparison test, let A and B be series with positive terms. The series here that's, and I guess it's arbitrary, but the A sub k series is given. And the B sub k series is the one that we pick. So that's up to us to specify or to choose. And then we're comparing those series to one another. And it says that if A sub k is less than B sub k, and the series that we chose converges, then A sub k converges. So then, I guess visually what that's saying is we have this series that we're choosing, whatever, it's B sub k, and it converges. So that series is converging. We're comparing that to the series that's given to us as A, but what we know is that A is less than B. So I'm going to draw a line here. I don't know, that's whatever that limit is. But all we know about A is that it's less than B. Or equal to. It'll just be on top of B, but if that's the situation, then what we know about the series is that it converges. So since it's smaller than a series that converges, it has to converge as well. Smaller than or equal to.
So if it is equal to, how do you know if it's converged or diverged?
By the one you chose, like if you know that the one you chose converges and that they're the same, right? If you like whittle it down or simplify it or whatever, you can see that they're equal. And then if the series that we've chose as B sub k is less than the series given and B sub k diverges, then A sub k diverges. So A sub k, if it's larger than a divergent series, then A has to diverge itself. A is larger than. So I don't know, something like this is A sub k is larger than B sub k. So basically what it says is if your series is smaller than a convergent series, it converges. If your series is larger than a divergent series, it diverges. So use the limit comparison test to determine if, the direct comparison test, if 1 over 3 to the k plus 1 converges. So when you choose that B, you want to choose, like, just think about like the asymptotic behavior as k gets large, or as n, whatever your index is, as that gets larger and larger, what would the numerator behave like and what would the denominator behave like? That's usually a good rule of thumb to choose a particular series to compare to. It's not always accurate, but. So here we would pick B sub k to be the sum 1 over just 3 to the k. And then whether we're using this comparison test or the other comparison test, it really depends on the series you chose. What does it do? So what does 1 over 3 to the k do? Converges. How do we know it converges?
Something like that.
Is what now?
Geometric.
Yeah. It's geometric with its ratio, well, I mean, I don't know that this is needed, but the absolute value of the ratio is less than 1. So we've chosen a convergent geometric series to compare to. All right, so that's step 1. Choose a series. You got to know if it converges or diverges. If you don't, then you've got these other tests we can rely on. But the series you choose, you have to determine if it's convergent or divergent. Then what we have to do is we have to relate A to B in some way. Is A larger than B or is B larger than A? So what do we know about 1 over 3 to the k plus 1 in relation to 1 over 3 to the k? As it approaches infinity, they're the same. right? But, yeah, this comparison test, when we directly compare two things, we're not looking at it in the sense of a limit. If we do, then that's a different test. So the 1 over 3 to the k plus 1 is less than 1 over 3 to the k. So since 3 to the k, 3 to the k plus 1 is larger than 3 to the k. All right, so that's what we need to do. We've got a comparison between the series given and the chosen series here, which converges. So the series in question, the 1 over 3 to the k, is less than the series for, 1 over 3 to the k plus 1 is less than the series for 1 over 3 to the k. So this sum is less than this sum. And we know this series converges. Right? So our series that we're dealing with is less than a convergent series, which means what? It also converges. Yeah, if the sum of 1 over 3 to the k is approaching a finite number, and we have something that's less than that, it also has to approach a finite number. Yeah, because when we look at a reciprocal, you have to switch the inequality, because right, it's 1 over a larger number is actually smaller than 1 over that number. Yeah. Okay, so since we have that inequality, the series we were given converges. Sometimes the test is not, it's not conclusive. The other downside to this test is that you have to compare two things, right? Like if you had something that was really quite involved, like what if we had like k cubed plus 2k squared minus 1 all over 3 to the k plus 1. If you had something like that and you were trying to compare that to 1 over 3 to the k, let's say, it's not a trivial thing to say which one's smaller or which one's larger. I mean, maybe that was a bad example, but you could see like certain situations where establishing that inequality is not a very straightforward thing to do. So the test we see after this is honestly preferred over this test because this test is inconclusive sometimes and the inequality or the direct comparison is sometimes hard to establish.
When would it be inconclusive?
So let's look at that when the direct comparison test is inconclusive. It's not that the other test we look at never comes out to be inconclusive, but it has a little bit more freedom to it, and we don't have to establish an inequality. So when is the direct comparison test inconclusive or doesn't work? Let's consider the sum from k equals 1 to infinity of just 1 over k plus 1 or 1 over k plus 2, whatever. So here we would probably pick our b sub k to be what? Yeah, just 1 over k. So we would pick b sub k to be this one. It's very closely related to that. Easy to establish inequality. But what do we know about 1 over k? Diverges. The harmonic series diverges. Okay, so the thing we're comparing to diverges. What do we know about 1 over k plus 1 in comparison to 1 over k? It's smaller. So this sum is less than this sum. But we know that sum diverges. You know, whatever. The sum is infinite. So the series that we're comparing to 1 over k, or with 1 over k plus 1 is less than the divergent series. So what does that mean? Nothing, right? It's less than a divergent series just means it still could diverge itself, or it might converge.
So basically, you don't have something good enough to compare it to.
Right, then you might try to compare it to something else. So we could revamp this and say, all right, well, is there something else I can compare to? Can I establish a relationship between, you know, an inequality between the thing that I'm comparing to if I have to revamp? So we'll just write this here, this series, at least in how we've chosen to test this, is less than a divergent series. So that doesn't tell us anything. What else wouldn't tell us anything? Right, yeah. If something is greater than a convergent series, that doesn't necessarily mean it converges, right? So it's basically saying like it's greater than a finite number. Well, all of these things are greater than a finite number. This is saying that our series sums up to something that's less than infinity. The direct comparison test is also inconclusive if the given series is greater than a convergent series. So it's not necessarily, it doesn't necessarily mean that the test won't work. It may just mean that you need to pick something else to compare it to. But the further you stray away from, you know, the kind of the form of the original series, I think the harder it is to, in a lot of instances, to establish a relationship between which one's larger, which one's smaller. Okay, so use the comparison test to determine if 2 over root k squared minus 3 converges. We can choose to keep that constant in, or we could take that 2 out. It doesn't affect convergence or divergence. So what should we compare this with?
2 over the square root of k squared.
2 over the square root of k squared. All right, seems reasonable. But that's the same thing as 2 over k. What do we know about the series for 2 over k? Diverges, because 2 over k rather. That is the 2 times the series of 1 over k, and we know that this diverges because it's the harmonic series. 2 times a divergent series still diverges. So okay, the series we've chosen is a divergent series. We just worked the 2 over the square root of k squared down so we could determine a little easier if it converged or diverged. However, when we go to make a direct comparison, we want to use the 2 over the root k squared to compare with, because it's more close in form to what we have. So our relationship here, the series that's given, in relationship to our chosen series. What's the relationship there?
The given is greater.
The given is greater. Do y'all agree with that? This is greater than. So if you're not sure, just start off with the k squares. We know k squared is equal to k squared, but k squared minus 3 is less than k squared. And then so when we take the square root of this, it still holds. Right? And then when we look at the reciprocal, we flip the inequality. So I don't know if it's hard to see, sometimes maybe you can sort of look at it piece by piece. And then of course multiplying through by 2 doesn't change anything. So the series is larger than a divergent series, which means what? Diverges. So I'll just write this out. Is larger than a divergent series. And thus diverges. All right, any questions on that? The limit comparison test then. Same kind of situation, you're given A, you choose B. This one also is hinging on the series that we choose. Do we know if it converges or diverges? But in this instance, we're not going to compare them directly, worry about which one's larger or smaller. All we're going to do is look at the limit at infinity of their quotient, see what that limit turns out to be. Based on what that limit turns out to be, situation 1, 2, or 3 tells us if it converges or diverges. Okay. So if we look at their quotient and the limit is finite positive number, then that means that both of those series do the same thing. Why would that be? Like why does that make sense? Or if it does make sense?
Because the tail is what determines the conversion.
Yeah.
So if they both end up, if the limit goes to the same place, then their tails are going to do the same thing.
Okay. Right. Yeah. And so then also, if if the limit goes to the same place, their tails are going to the same place. Is that?
So either they're both converging or they're both diverging.
Okay, yeah, and what would it mean, like, if let's just say that this limit is equal to 2. Like, if I compute that limit and that limit is equal to 2, what does that mean about A and B in comparison to one another? A is greater than B? Okay, maybe initially, right, but we're looking at the limit at infinity, so that means, like, as we get way out here, how does A and B grow compared to each other? If you have a finite positive limit, they grow pretty much the same rate, right? They're growing at a comparable rate. Like, just think of that function, right? 2x squared over x squared. The limit at infinity of a function like that is a finite number. It's 2. So they're growing at comparable rates. So if the series that we've chosen grows comparable compared to the series that was given, then that means that they do the same thing, right? The series chosen converges, the series given converges as well, because they are growing at comparable rates. Okay, how about situation number 2? If the limit of their quotient is equal to 0 and the chosen series B converges, then A converges. So why does that have to be this case? If the limit is 0, the series we chose has to converge to imply convergence on A. If that limit is 0, what does it mean about A and B? B grows more rapidly than A. And so if we have a series that grows much more rapidly than A, and we know that series converges, right? Like here's B, it's converging really quickly. And then maybe A does this. Right? So B is growing much more rapidly and we know it converges, therefore A has to converge. Does that make sense? In terms of like growth rates. Okay? And then the third condition is if that limit is infinite and B diverges, then A diverges. So in that instance, if this limit is infinity, that means A grows much more rapidly than B. And if B diverges and A is growing more rapidly than a divergent series, then it has to diverge as well. Okay, so the nice thing about this comparison test is that you do not have to establish a relationship between the two series. So this limit comparison is preferred over the direct comparison. I think in practice it's probably even easier to use. You don't have to think about relating two things to one another. So the comparison test to determine if this converges. Now again, what would we choose, whether we're using the direct comparison or the limit comparison? What would be a good choice for the series that we're picking to compare to? 1 over the square root of k? What do y'all think? So what do we actually have? We have a k on top of the series that's given. We actually have as the leading term on the bottom, root k times 3k, right? So let me scoot this. We have 3 times k to the 3/2 minus 5 times k to the 1/2 as the given series. So does that change our mind? Maybe, maybe not. So we're going to choose that to be, maybe initially we say, all right, well, I'm just going to look at the leading term over the leading term. Which is the same thing as what? Well, would it be, so would it be k, 1 over k to the 1/2? Or, yeah. So this is, if we're going to use the direct comparison, we need to stick with that because it's more similar to our original series. But we're kind of whittling this down so that we can use some other test on a kind of a simpler series that's related or closely related, I guess. All right, so that's what we're going to choose then. What do we know about 1 over k to the 1/2?
It diverges.
Yeah, how do we know it diverges?
Yeah, P series.
It's just a p series, right? So it's not only like with these comparison tests, not only do you know, even if it's like, hey, I'm going to choose this series to compare to, you got to make sure that you know if it converges or diverges. And sometimes that's not straightforward. Maybe you have to take the series you're choosing and like take it off to the side and look at an integral test to determine if the thing you're choosing actually converges or not. Okay. All right. So we'll just say this divergent p series. And we'll look at that, we'll look at how this kind of unfolds next time. Do y'all have any questions before we go? All right, see ya.